Welcome to our lecture online, and now we're going to talk about how we can find the distance to stars if we know both the absolute magnitude and the apparent magnitude. Remember, the apparent magnitude is how bright the star appears to us from the Earth. The absolute magnitude is equal to what the apparent magnitude would be if we place the object, in this case the star, at the standard distance of 10 parsecs away from the Earth. So here we have an observer looking at a star. There's certain apparent magnitude. In the case of Betelgeuse, the apparent magnitude of the star, the way it looks to us from wherever it is, has a magnitude of plus 0.58, which still makes it one of the brighter stars in the sky. But if we were to place it 10 parsecs away, it would have a magnitude of minus 6.02, which makes that the absolute magnitude. Since the absolute magnitude is minus 6, that makes it a very, very bright star. Remember, our sun, if we place our sun over here, its absolute magnitude would only be a plus 4.8. So minus 6.02 is much, much brighter than a plus 4.08. All right, so now what we're going to do is, based upon that information, we should figure out where Betelgeuse actually is, how far it actually is to Betelgeuse. So starting out, putting Betelgeuse over here, it would have an absolute magnitude equal to minus 6.02. The fact that it has a dimmer number wherever it is, so the apparent magnitude is actually a plus 0.58, that means it must be a lot farther away than 10 parsecs. If it's dimmer, if its apparent magnitude is dimmer than its absolute magnitude, it must be farther away. The question is, how much farther? Well, the way we do that is as follows. First of all, you find the difference between the magnitudes. In other words, we take, in this case, the apparent magnitude minus the absolute magnitude, and in this case that would be a apparent magnitude of plus 0.58 minus a minus 6.02. So the difference in magnitude between the apparent magnitude and the absolute magnitude is actually a 6.60. That's the difference in the magnitudes. All right. So what we do with that now is we go ahead and find out what that means in luminosity. What is the difference in luminosity if the magnitude is 6.6? And there we can say that the difference in the luminosity, the difference in the intensity or luminosity, is equal to 2.512 raised to the delta m. All right? So that would be equal to 2.512 raised to the 6.6 power. If we then grab a calculator, figure that out, 2.512 raised to the 6.6 power is, see here, 4,000, wow, I need my glasses for this one. It's too dark for me to see. 436.646. 436.646. So that is how much dimmer it appears where it actually is compared to what it is or what it would be if we place it 10 parsecs away. Or you could say, if we take Betelgeuse, which must be way out here somewhere at a very far distance, if we take Betelgeuse and bring it to a distance of 10 parsecs away, its intensity or luminosity would increase by a factor of 436. It would be 436 times brighter at 10 parsecs than where it actually is. Now to find the distance is equal to 10 parsecs multiplied times the square root of the difference in the luminosity. So now we take this number right here, take the square root of that, and multiply times 10 parsecs, and that's where Betelgeuse actually is. So let's work that out. So the distance to Betelgeuse is 10 parsecs times the square root of 436.636 or 646. Not that those decimal places really make much of a difference for us. So let's take the square root of that. Okay, and let me show you what that is. So that's equal to 10 parsecs times the quantity 20.9. And so that would be equal to 209 parsecs. So that would be the distance to Betelgeuse. Converting to light years, then we have to multiply this times a ratio of 3.26 light years per 1 parsec. And so multiply times 3.26 equals, and that would put it at about 681 light years, which is right around the distance that we currently know Betelgeuse is. It's very difficult to get accurate readings on where things are, especially stars, but that is fairly accurate to the point where we know that it's right around 680 light years to Betelgeuse. So, again, the absolute magnitude is the brightness an object, in this case the star Betelgeuse, would be if we place it 10 parsecs away from the Earth. So this distance is 10 parsecs. The fact that the apparent magnitude, it's much dimmer, then we know that Betelgeuse actually is much further away from us. How do we find that distance from the Earth to Betelgeuse? Well, what we do is we take the difference in the magnitudes. The difference between minus 6.02 and plus 0.58 is 6.6. We then use that we then use it as the exponent of the number 2.512 to convert from the difference in magnitude to the difference in luminosity. Luminosity is the brightness in terms of watts per square meter. So we then raise 2.512 to the difference in magnitudes, and out comes 436. That means that Betelgeuse is 436 times brighter if it was at a distance of 10 parsecs compared to where it actually is. We then find the actual distance by taking 10 parsecs and multiplying it times the square root of the difference in luminosity, which is the number we got right here. We plug that in here, and I keep forgetting to put the end parentheses there. So the square root of 436 is about 20.9. 10 times 20.9 is 209 parsecs. Converted to light years is about 681 light years. And that's how we find the distance to any object, any star, galaxy, whatever it may be, using this particular principle. That's how we do that.